Hello. This lecture is for section 2.1 of Math 311. It's a course in linear algebra at Western Illinois University, and the topic is Introduction to Systems of Linear Equations. Okay, so we just finished chapter 1, where we learned about lines and planes and how they and the equations to describe lines and planes. And we're going to keep talking about those and lead that into our discussion of systems of linear equations, because linear equations, these are equations that basically define either a line or a plane or a hyperplane in bigger dimensions. And we're interested in when do these things intersect. In fact, in particular, when do two lines intersect? How do two planes intersect, and so on. And we can sort of see all this already, especially in terms of lines. We know that if we have two lines, then they either meet, right, or they don't meet. That is, they're parallel, and or they could be the same line. Okay. There's no other way you can. There's no other alternative, right, when you're dealing in lines in R2. Now, if we talk about planes in R3, if you think about it, there's some more possibilities. It could be, you could have planes that are parallel, which don't meet at all. That's with two planes, if we're talking about two planes here. Or we could have two planes that intersect. And we sort of indicated this last chapter, and we're going to prove it today, that these planes will intersect in a line. The other alternative is that the planes are exactly the same. Okay. There is no possibility where two planes intersect at a point. All right. If you think about that, because these planes, I've drawn them as they look like finite things, but they actually go on for infinity. Okay. So let's look at these finding where find these intersections really boils down to solving a system of linear equations, so what we're going to do some examples, and we're going to try to do this with just looking at the systems of equations and not necessarily looking at them graphically. Okay, so here, for example 1, I actually have 3 examples here, and in both these cases, we're going to assume that we're working in R2, and we know that in R2 all these are equations of lines. They're just in general form. Now, and we're basically solving this system boils down to where did these lines intersect. Now, I think we have some experience. Maybe you already have some experience of solving equations with two equations and two unknowns. All right. There's a couple ways we can do this. We can do something called back substitution, where we write one variable in terms of the other. Like in this case, we could write y. I take this first equation and write y equals 1 minus x, and then substitute that into the next equation, where we would get x plus 2 times 1 minus x equals 3. Okay, and then if we go ahead and substitute in for x, we get x plus 2 minus 2x equals 3, and so this would be minus x plus 2 equals 3. Minus x is minus x is 1, so x would have to be negative 1, and then plugging in negative 1 into y would be 1 minus negative 1, which is 2. Okay, so we would get the point negative 1, 2, and sure enough, that would be our point of intersection. We could also, so this is called back substitution. Another way we could have done this is we could have multiply one of the equations by -1 and add it to the other, and then that would eliminate a variable, right? We could multiply the this equation by -1. Okay, we do that. Then the x's would cancel. When we add these, we can add two equations together, because if we're assuming if both equations are true, then we can add them together and get another true equation. So in this case, we would get that a negative y. This would be negative y plus 2y. That would be y. And then this would be -1 plus 3. That would be 2. So we get y equals 2, and then we can plug back in here and get x equals -1. Okay. So this is a case where we have two lines that intersect, okay, at a point. Now, in this next example, I think you can see that here, well, if we try to do the same thing here, and write, let's say, y equals 1 minus x again. And if we plug that in here into the second equation, we get 2x plus 2 times 1 minus x equals 2. Okay. And then we can say we get 2x plus 2 minus 2x equals 2. And then minus 2, the 2x's cancel, and we get 2 equals 2. And that doesn't really give us anything, right? While this is true, this doesn't really tell us what x and y should be. But in fact, it does, because I think you can see that one equation is a multiple of the other. So these two equations really describe the same line. Okay, so you basically, when this is a case where there are going to be infinitely many solutions, where x can be anything we want, and y is just going to be 1 minus x, and we have infinitely many solutions. Okay. Now, in the second case, the last case here, we can see that there's going to be no solutions, right? Because if we try to do this, say y, do the same thing, y equals 1 minus x, we substitute that in here, we get x plus 1 minus x equals 2, and then get 1 equals 2, and that can't happen, right? So there's no solution. And of course, we can see right away that there's no way that 1 can equal 2, so this has no solution. And what happens if you were to look at these lines, these would be two parallel lines. Okay. All right. This would also be called an inconsistent system of equations. Okay. Now, if we go to if we go to another dimension, okay, now let's go to R3. Okay. What here? These two equations are equations of two planes in R3. Okay, and let's see if we can solve this system to get a solution here to see how these planes intersect if they do. Okay, well, we can do the same thing with back substitution. We can write one variable in terms of the other. And I'm just going to pick z with this first equation here. We can see that z from this first equation, subtract x and y from both sides, and z is 1 minus x minus y. And then we can plug that in here. Then we get minus x plus y plus z, which is 1 minus x minus y, is equal to 3. Then this will simplify. This is minus 2x. So the y's cancel, and we get plus 1 equals 3. So minus 2x equals 2. So x has to be -1. Okay. All right. So that means if this does have a solution, then we're just going to have then x has to be -1, no matter what else happens. Okay. All right. So now we found out that. So what can we do now? We can plug in this value and for -1 into one of these, right? And so we can see that, well, actually we can plug this value up here, and we'll get that z is equal to 1 minus -1 minus y. So z is going to be 2 minus y. Okay, and then All right. So at this point, what can we do? Well, we can, if we try to find out what y is, maybe using our last equation here, we'll see that x is still -1 plus y plus z, which is 2 minus y, equals 1. And we get this from plugging it in here. And when the y's cancel, we just get 1 equals 1. So that doesn't help us, but actually it tells us that something is, that this actually is going to have inflammatory solutions. As long as z is equal to 2 minus y and x is equal to -1, y can be anything we want it to be. So actually what we get, our solution would be x equals -1, y equals y, and z is going to be 2 minus y. And if you were to replace this y with a t over here, these are just the parametric equations of a line. Okay, so we have these two planes intersect in a line, and the line is given by this, right? We could, in fact, particularly, we could write this as -1 plus 0t, y is equal to t, and z is equal to 2 minus t. Okay, that would be the line of intersection. Okay, let's look at another case. Well, an example which is almost the same, but we can when we just change a minus sign here, and we can see right away that this is nonsense, right? There's no way that 1 can equal 3. So this is there's no solution here, or it's inconsistent because 1 does not equal 3. And in fact, what we have, this corresponds to parallel planes. They don't intersect. Okay, well that was easy enough. Now, going on to 3 equations, let's look at let's add a variable and look at example 4. Now here considering these solutions as points in R4, or vectors in R4, where in this case our variables will be x, y, z, and w. And if we try to do, we can try to do the same thing as we did before. We can write w in terms of x, y, and z. In fact, we can take this equation and write w will be x. You basically add w to both sides of the first equation and get w is equal to x plus y plus z, and then plug that into the second equation, and we will get 2x plus y plus z plus x plus y plus z equals 1. If we add this together, we get 3x plus 2y plus 2z equals 1. All right. Well, that is what can we do with this now? If we have a relation now between x, y, and z. We can use this last the other equation here, going back up here. We can stick with this, and we can write z in terms of x and y. We can say 2z will be 1 minus 3x minus 2y, and divide by 2, so z will be 1/2 minus 3/2 x minus y. And now we can see that both w and x can be written in terms of x and y, right? W is now going to be x plus y plus 1/2 minus 3/2 x minus y. Okay, so w is going to be 1/2. X minus 3/2 is, this will be minus 1/2 x, and y minus y is 0. Okay, all right. So our solution will look like this, and now we have not only do we have we have one free variable, but two free variables. X and Y can basically be anything we want it to be. So the solution will be given by, we can let x equals x, y equals y. Z will be 1/2 minus 3/2 x minus y, and w will be 1/2 minus 1/2 x. Okay, all right. Okay. You could also write this as a vector equation. You can write this. We can actually write the solution as x, y, z, w can be written as the constant vector 0, 0, 1/2, 1/2 plus x times the vector 1, 0, negative 3/2, negative 1/2 plus y times 0, 1, negative 1, and 0. Okay. All right. And this, we're going back to now this will actually correspond to a two-dimensional thing in R4. We just can't see it, right? Okay. Let's go back to R3. And now look at what looks like three planes, and we like to say how can three planes intersect? And just to think about this for a moment, if you have three planes, they might not intersect at all, but they could intersect in a line, or they could intersect at a point, or they could be just all the same plane. So most of the time, what we'll have, let's say, if we have two planes, if they intersected a line, this third plane will either go through this line or it won't. So we could have something like this, where the intersection is a line, or we could have a point. They might intersect at a point. We have something like this. Okay, where just have a point. And if the easiest way to think about that, if you're in multivariate calculus, you just look at the xy plane, the xz plane, and the yz plane. They intersected at the origin, right? And again, all three planes could be the same as well. Okay, so what happens in example 5? Now here, this is a particularly nice example because this last equation, it's very easy to solve for one variable and then plug that back in. So the back substitution works very nicely. We can see from here that z has to equal 3. And then plug that back in here, we get 2y plus 3 equals negative 1. So that means subtract 3 from both sides, we get 2y equals negative 4. So y has to be negative 2. And then plug those two values back, and we get x plus negative 2 plus 3 equals 1. And that tells us that x has to be 0. Okay, so the solution to this would be x equals 0, y equals negative 2, and z equals 3. Or we can say that they intersect, the planes intersect at a point. At the point 0, negative 2, 3. Okay. All right. In example 6, if we try to do the same thing, we look over here and we can see like the least threatening equation would be the middle one, because we can write z as negative 1 minus 2y. We subtract 2y from both sides. And then we'll plug that back into either equation. We'll plug that back into the first equation and get x plus y plus negative 1 minus 2y equals 1. Simplifying, we get x minus y minus 1 equals 1. So x minus y is 2, and we can write x is going to be y plus 2. And then finally we can plug that back in here and see what happens here. We get, well, we can replace x with y plus 2 plus 3y plus 2z, and z is still negative 1 minus 2y equals 0. And if we try to simplify this, this is y plus 2 plus 3y minus 2 plus or minus 4y equals 0. And you'll see everything cancels out, right? And we get the amazing fact that 0 equals 0. So once again, this sort of indicates that y can be anything we want it to be as long as x is equal to y plus 2 and z is equal to negative 1 minus 2y. So our solution would be x is y plus 2, y would be y, and z is negative 1 plus 2y. And so once again, we get a line in R3, which is the intersection. Okay. Now, one thing before we move on, one thing that you might have noticed here is that if we add these first two equations together, we get the third. Whereas that's not the case. That's not the case in our example. In fact, there's no way you can there's no sum of any two equations here that's equal to the third. Okay, and that should sort of give us away that this third equation is a little redundant. Okay, this is third, or if you will, dependent on the first two equations, right? So that kind of gives you an sort of explains why we're getting an extra dimension here. Okay, and the more redundancy we'll see on these equations, the bigger the solution set will be. Okay, to bring everything together, we'll finally give you the definitions here, because we'd like to generalize this to other dimensions here. So we say a linear equation in n variables, x1 through xn, is an equation of this form, where we have something times x1 plus something times x2 plus and so on plus something times xn equals a constant, where these a's are and the b are just constants, or in this case we're going to assume that they're just real numbers, but they're constants, and these are the variables. We use this a lot of times. We use this instead of x, y, z, because a lot of times we don't know how n is. We might, n might be a very large number, and there just aren't enough letters of the alphabet to use, right? So we'll just use these variables with subscripts. And again, these are the constants. These a's are called the coefficients. Okay, and what we're really looking at is systems of linear equations, and we say an m by n system of linear equations consists of m equations and n unknowns, or n variables. So we have something like this. So we have these m equations where we have something times x1 plus something times x2 and so on equals a constant b1, and then we have another equation and another equation like that. And each equation corresponds to a hyperplane in Rn. Okay. So basically, this one equation describes a hyperplane in Rn, and this system talks about how these hyperplanes intersect. Okay, all right. So we're going to spend a lot of time talking about how to solve these linear equations, without doing a lot of this messy algebra. But the way we're going to do this is that we're going to see that as long as the equations are lined up, the coefficients are really all we need. We don't need to keep writing these variables all over. So each system is going to correspond to something called an augmented matrix. And this basically takes the system of equations and just eliminates the variables. And it just keeps the coefficients and the constants. A matrix, of course, is a rectangular array of numbers. And in this case, for the augmented matrix, we just take the coefficients of the first equation with the constant. And then the second row is the coefficients of the second equation plus the constant, and so on. Okay. So every system will have one. So just to go back and look at our examples, let's say, for example, 2, the augmented matrix would consist of 1, 1, 1, 1, because this is 1 times x, 1 times y, 1 times z equals 1, and this would be negative 1, 1, 1, 3. And we put a line here to divide to indicate that these are the constants, constant terms. For example, 3, or maybe I should go up here and say that for this one up here, the augmented matrix would be 1, 1, 1, 2, 2, 2. For this, it would be 1, 1, 1, 1, 1, 2. For example 3, the augmented matrix would be 1, 1, 1, 1, 1, 1, 1, 3. For example 4, the augmented matrix would be 1, 1, 1, negative 1, 0, and then 2, 1, 1, 1, 1. And then here, the augmented matrix would be 1, 1, 1, 1. Now, the only tricky part here is there is no x term, but actually there is, because we can see a 0x here. And we can see this would be 0x plus 0y here. So this would, the next row would be 0, 2, 1, negative 1, and then 0, 0, 2, 6. And similarly, the augmented matrix, for example 6, would be 1, 1, 1, 1, 0, 2, 1, negative 1, and 1, 3, 2, 0. Okay. Right, now, and here once again we can clearly see that the sum of the first 2 rows is equal to the bottom row, okay, which is going to, sometimes we can see that relatively easily, so a lot of times we can't. But the thing here, obviously, is we would love our augmented matrix to be as nice as possible. In fact, we would love it if our augmented matrix was something like 1, 0, 0, 0, 1, 0, 0, 0, 1, is 5, 7, 3, something like that. Because in that case, we can basically read off our solutions. Okay, this corresponds to saying x equals 5, y equals 7, z equals 3. Okay, or something maybe a little more difficult, but just as interesting, like 1, 0, 1, 5, and 0, 0, 1, negative 1, 4, something like that. Because that would correspond to a matrix like x plus z equals 5, y minus z equals 4, and then you could write everything in terms of, you could write z in terms of x and y, right? And then you could, then things are real nice. These last 2 matrices, at least the left part of the matrices, they're in a very particularly nice form called reduced row echelon form. And what we're going to learn in the next section, or the next 2 sections, is how to transform our augmented matrix into a matrix like this, where we can basically read off the solutions. Okay, so that's what we'll be doing in the next section.